Hello, my name is Luís Pessoa and I work here at Tech. And today I will be presenting you our iBROW demonstrator using RTD-PD. So I will start explaining the experimental setup used for this proof of concept demonstration. So we are using a laptop as a signal source, as a video source. We are actually using the HDMI output of the laptop, and we are using it connected to a DVB-T modulator. So this modulator takes an HDMI input and modulates it using the DVB-T standard, which is based on OFDM, and modulates it onto a subcarrier. So in this case we are using a subcarrier frequency of 150 MHz, and we are using 64 QAM, so we are using DVB-T standard parameters. So the output signal from this modulator is then interfaced to a laser. To do that, we use an amplifier which is working as a driver to condition the signal to the laser. So we have here the driver, and then we have here the laser. The laser, it's provided by iBROW partner CST, and it's a 1310 nanometer laser, and it is being biased through this bias T, and it is actually biased using a current source which is actually at 34 milliamps right now. So the signal from the laser is then injected into an optical fiber, to a single mode fiber, which is connected to the RTD. So the RTD-PD, it's assembled here on the BROW station, and the fiber that is coming from the top, it's actually aligned on the top window of the RTD-PD. And so we also use two RF probes. So an RF probe on the right, which is used to DC bias the RTD. So the DC bias, it's actually provided by a power supply. In this case, as you can see, we are using a bias voltage around 1 volt, and the RTD-PD is consuming around 250 milliamps. So the RTD-PD, it's biased within its NDR, so it's negative differential resistance region, and it is oscillating at around 13 gigahertz. So this 13 gigahertz signal then comes out of the RTD through this RF cable, and it's connected to a set of equipments that are here. So we have a signal generator and the signal analyzer or spectrum analyzer. So the signal generator, it's used to injection lock the RTD-PD at its output. So we use an electrical circulator. So the signal comes from the signal generator, goes through the circulator, goes into the RTD, and then the RTD signal that comes from in this direction will pass the circulator into the signal analyzer. The signal analyzer, it's actually working as a down converter. So it is converting the 13 gigahertz signal to an intermediate frequency. In this case, the intermediate frequency of this equipment, it's 322.5 megahertz, and it's a connector on the back of the equipment. So we have an RF cable connected on the back of the equipment that is coming here, and through an amplifier that is right there, it's connected to the TV. So the TV, it's actually we are using the RF input of the TV, so we are using its built-in DVB-T tuner. So it is actually receiving directly the signal that is coming from the spectrum analyzer at 322.5 megahertz. So as you see in the tuner here. So you see here the levels of signal strength and quality, and you see that the video is working perfectly. You see the sound, and you see the quality of the image. So it is working perfectly well. Okay, so I can also show you here on the spectrum analyzer the spectrum of the signal. If I do that, I will disable the IF output. So if I show you the spectrum of the signal, the IF output will be disabled, so this video will stop, and you can see on the screen the RTD carrier and the subcarrier modulation on the right side and another subcarrier on the left side. So we have two sidebands which are automatically generated when we modulate the RTD with a RF subcarrier. If I press the zero span again, I will activate again the IF output, and the video will play again. I can also show you what happens when we decrease the power of the signal generator that is being used to injection lock the RTD. So if I come here and I decrease it, it will have an impact on the quality until it completely stops the video. So I need to ensure a minimum power in order to enable the video transmission also, which means that it is required in order to injection lock the RTD-PD to reduce its phase noise. This demonstration, it's actually a proof of concept of the ability to modulate the RTD-PD with an optical signal, subcarrier based signal, and to transfer this signal to the RF domain, in this case 13 gigahertz. But it shows ultimately it shows the possibility of using the RTD as an interface between optical networks and the wireless domain in the future, possibly at very high frequencies. And this concludes the presentation. Thank you for watching.